Okay, today we are going to discuss the case of kinematics when it comes to air resistance. So the norm is that we discuss all the kinematics equations with no air resistance. So before we start with the air resistance case, let's review what we already know in the no air resistance case. Okay, so here we have a ball thrown up with initial velocity v0. Okay, in the case of no air resistance, the only force acting on the ball must be mg. Hence, this is also its net force, and the acceleration caused by the net force is downwards. Right? As the ball goes higher, right, it starts to lose velocity because the acceleration is downwards, so it's slowing down or decelerating. But the magnitude of the net force remains the same because the only force acting on the ball is still mg. When I hit the top of the flight, okay, my velocity is 0. Again, my net force is mg. So you can see all the way up, my net force is a constant value, which is equal to the weight of the ball. As the ball starts falling down, right, at this position v3, similarly the net force does not change. Okay, so we can see throughout the motion, no matter at which position the ball is, the net force acting on the ball doesn't change. So in the case of no air resistance, my Fnet is mg, and I equate my Fnet to be ma, this is Newton's second law. Alright, so my acceleration must be equal to g by virtue of this equation, and that's why my A is always 9.81, as we have discussed in kinematics. If we were to draw a graph of velocity against time, okay, it will be a straight line graph starting from a certain velocity here, where this value of velocity is equal to v0, the starting velocity. Okay, it will be a straight line with gradient 9.81 or negative 9.81. Okay, and when we look at this graph, there are a few things we need to pay attention to. Firstly, that the distance traveled in the vertical direction upwards can be given by this triangle over here, right? Because area under graph for VT graph is actually the change in displacement. And for me to come back down to my starting position, I must cover an equal and opposite negative area. Alright, so here the change in displacement is negative. The area is equal to the change in displacement here, which is positive. Right, so S up must be equal to S down. Okay, the displacement outwards must be equal to the displacement downwards. Okay, so because of the constant gradient, we can see that this time taken for it to hit the highest point must be equal to the time taken for it to come back to its original position from the highest point. Okay, so that's the idea where there is no air resistance. We then approach the example with air resistance. Okay, what's the difference with air resistance? I do the same thing, I throw the ball up with a velocity v0. I'll find that now the force acting on the ball is not just mg, but also kv squared. Okay, where kv squared is the drag force acting on the ball as a result of its velocity. Right, k is a constant value. V is actually the velocity of the ball at the point of time. Right, so this can be written as kv0 squared. Okay, as it goes higher and higher, my net force is acting down, so my acceleration is downwards. This means that since my velocity is opposite in direction to my acceleration, my velocity must drop. Okay, so when this velocity drops, what happens is kv squared, where kv squared is a force, actually also drops together with the velocity. Okay, so as you go higher and higher, actually your drag force starts to reduce, simply because drag force is proportional to velocity, and your velocity keeps dropping all the way to the highest position. And when we look at the highest position, there will be no longer any drag force, simply because the velocity at the highest position is 0. As the ball comes down, the idea changes a bit, because now the velocity of the ball is downwards, directed downwards, hence the magnitude of the drag force must act upwards. Drag force always acts opposite in direction to the motion. Okay, so as it further goes down, because in this case the weight is greater than drag force, we know that the acceleration is still downwards and the velocity must increase. So as I go from v3 to v4, the magnitude of the velocity increases, and hence kv squared, the magnitude vector, must also increase. So as you can see, when I go from this case v3 to v4, actually my net force downwards drops because mg remains the same. However, kv squared increases, but increases in the upward direction. So my net force downwards actually drops from v3 to v4. Okay, we'll see the consequence of this in an equation. Alright, we first look at the going up case. Okay, the F net when I'm going up is equal to mg plus kv squared. Right, so mg plus kv squared equals to m acceleration outwards. And if we manipulate the equation a bit, I realize that acceleration outwards equal mg plus kv squared divided by m. And if I do a simple simplification of the formula, is equals to g plus kv squared over m. Now, kv squared over m is a positive value. I know because I'm sure of the direction of my net force. I'm sure of the direction of my drag force, which is downwards. So I know kv squared is a positive value, hence this whole value over here is a positive value. By extension, I know that acceleration upwards is greater than the value g, okay, which is 9.81. So I know that on the way up, when the ball is moving on the way up, just before I hit the highest position, okay, my acceleration when I'm going up, when the ball is going up, is always greater than the value 9.81. Okay, the direction of A up is actually downwards. Okay, this means acceleration on the way up. Okay, let's look at the coming down case. For the coming down case, it's a bit different because my F net is no longer mg plus kv squared. Because if you look at the free body diagram of the ball, my F net now is mg minus kv squared because they are in opposite directions. Alright, so therefore we can get acceleration downwards to be mg minus kv squared divided by m. Okay, a simple manipulation, you'll get this value, and you realize that when I'm coming down, in the case where there is air resistance, my acceleration of the ball on the way down is actually smaller than g, because it's g minus a value that is positive. Okay, so now we come to a conclusion that on the way up, my acceleration keeps reducing, right? Because when I go from v0 to v1, my net force drops all the way until this value. And then when I'm coming down, my net force still reduces. But you can see the greatest net force is actually at v0, where the net force is equal to mg plus kv squared. Right, then I drop, because my velocity dropped. I drop all the way to mg because there's no more drag force at zero velocity. Then as I'm coming down, I drop further. The net force value drops further because now the kv squared is opposite direction to the mg, as opposed to this case where it's in the same direction. Actually the magnitude of the net force gets bigger. Right, so here the magnitude of the net force is smaller than mg. Okay, and it further drops as my kv squared increases. So all the way throughout the motion, my net force drops, and the magnitude of my acceleration drops as well. Okay, so my highest acceleration is at the start for the case of air resistance, and the lowest acceleration is when I'm at the starting point. Okay, let's see how this works out in a graph. Okay, so the graph looks a little bit complicated, but nevertheless we'll try to understand what is going on. Okay, this is v0, which is the starting velocity when I'm thrown up. Okay, so at v0, if there were no air resistance, I would draw a straight line graph as per this situation, because this would represent a gradient of negative 9.1, right, if there were no air resistance. However, we know that in the case of air resistance, my acceleration magnitude is greater than 9.1, right, because the net force downwards is greater than just mg. Okay, so we know that the acceleration value is greater than 9.81, and so the magnitude of the slope must be greater. Okay, what we mean to say is that this curve over here, the slope at this point where t equals to 0, the steepness must be greater than the 9.81 gradient line. Alright, so that's why it is sharper, it's more steep at this position. Okay, as time progresses, we know that as velocity drops, the net force downward drops. Right, from the equation above, we can see that as kb squared drops, my acceleration on the way up, the magnitude actually drops as well. So I drop all the way, right, so I get less and less steep until this position, which is a special case because at this position, my velocity is 0. I know I'm at my highest point. At my highest point, which is here, okay, I realize that the only force acting is mg. Hence, the acceleration at this position must be 9.81 because the F net is mg, right? So my A must be 9.81. So at this point, if you ever to sketch a graph, take note that this gradient should be equals to negative 9.81. Okay, and then we further move on. After that, you realize that the net force drops even more as I come down from my highest position, and hence my magnitude of acceleration drops further. Alright, I drop all the way until I maybe hit terminal velocity. Whether or not I hit terminal velocity depends on many factors. Alright, but in the case that I approach a straight line over here, it means I have hit terminal velocity, where terminal velocity is the case where the kb squared equals to the mg, and there is no net force, hence the acceleration is 0 and my velocity does not change. Okay, so a few interesting things we can learn from this graph is that firstly, because of air resistance, when I compare the no air resistance case, which is this line, versus the air resistance case, which is this curve, okay, I realize that if I start with the same velocity, the case with air resistance must necessarily cover a smaller height, right? Simply because of the area under the graph. The blue area here is definitely smaller than this large triangle that would be the displacement covered if I had no air resistance. So the first thing you observe is that there's a smaller displacement when there is air resistance, okay, as opposed to the case where there is no air resistance, simply because the downward acceleration is higher. Okay, so that's the first thing we'll observe. The second thing we observe is that, as discussed previously, at the point where velocity is 0, I realize that the acceleration here must be 9.81, and hence the gradient here must be negative 9.81. Alright? And then finally, we want to look at an example of an A-level question, whereby they ask, explain why for all real vertical throws. When they talk about real, they mean that in real life. Okay, so you need to take the case where there is air resistance, because in real life there is air resistance. Okay, so explain why for all real vertical throws, the time taken to reach maximum height must be shorter than the time taken to reach the starting position. Okay, what it means to say is that, can you explain why this time, okay, the time taken to reach its maximum height is greater than the time taken to come back to my starting position? Right? We can explain this idea by two ways. One is graphically. Alright, if you look at the shape of the slope, you realize that because the gradient gets less and less steep, alright, I actually cover a lot more area here, the blue area, in a shorter span of time, as opposed to when I go underneath the x-axis, because of the shape of the graph. Right, so for me to cover a same area as this blue area over here, which is the displacement covered upwards, right, for me to come back down, I must cover an equal displacement that is negative, right? So I should take a longer time, simply because of the curvature of the graph. But I cover less displacement here per unit time as opposed to here. Right, so that's one way to look at it from the graph. But if we were to require a worded explanation as per what this question is asking, okay, we can see that we can explain from this diagram itself. Right, on the way up, okay, the resultant force, the average resultant force, and hence the average acceleration, okay, I missed the word here, average acceleration, downwards, is much greater than the average resultant force and average acceleration downwards on the way down. Right, so on the way up, my average force is greater, and hence my average acceleration is greater than on the way down. And because of this, the average velocity upwards, okay, this average velocity upwards must be greater than the average velocity downwards. Okay, since they cover the same displacement, right, for the same displacement, the time travel upwards must be shorter than the time taken to travel downwards, because the average velocity when I'm moving up is greater than the average velocity on the way down. Okay, you can see that from here to here, I go from a value v0 to 0, but on the way down I go from a value 0 to a value v4, where v4 is actually smaller than v0. Okay, and so if I look at on the way down, the average velocity is definitely smaller than the average velocity on the way up. And so for the same displacement, the one with greater average velocity on the way up must take a shorter time. Alright, so that's a overview on kinematics with air resistance. Do note that this is not a replacement for your notes. Please do read your notes as well. Okay, there will be a practice question uploaded underneath this video for your use.